All right, discrete mathematics. This video is an introduction to section 5.1, which is about mathematical induction. Mathematical induction is a proof strategy that is used to prove a particular type of proof, type of claim, namely claims that something is true about all natural numbers or about all positive integers or some other elements of some other set kind of similar to those. So it's a strategy that is kind of, it's sort of falls into the umbrella category of recursive structures. So this is a proof strategy that employs an idea of recursion. And so we're going to start with that. And then later in chapter 5, in section 5.3, we're going to study recursive structures more generally and look at a few other examples of how to define things like sets or sequences recursively. So let's start with an example. This example says if n is any positive integer, then when you add up the numbers from 1 to n, it results in the sum n times n plus 1 divided by 2. This is a summation formula that you may have seen in the calculus class or in a pre-calculus class when you studied things like arithmetic sequences. In calculus, it comes up when you study integrals, like the sort of the more formal definition of an integral, doing integrals the long way with the limit of a Riemann sum. So anyway, when it's introduced to you in the past, you may have been given it without any form of proof, or you might have been shown a proof, but you probably weren't shown an induction proof. There's other ways to prove this formula. Anyway, I'm going to show you a proof of this formula using this strategy, mathematical induction. Proof by induction. All right, so a proof by induction always starts with something called a base case. Base case is where you take the first value of the variable, whatever starting value it is. In our case here, it's going to be n equals 1. But in other claims, you might have n starting at 2 or at 3 or at 4 or whatever. It just sort of depends. It'll tell you in the claim, it'll say for all positive integers n greater than 2 or something. If you were given that, then you would start with n equals 3. All right, so for our case, we're starting with n equals 1. Now what I want to do is essentially prove, I want to prove that this claim is true for n equals 1. And to do that, I'm going to just label the left side as L and the right side as R. So I'm using those labels just so that I can check the value of the left side and the value of the right side and confirm that they're equal. So for n equals 1, the left side is going to equal 1, and that's it. Because if you're adding up the numbers from 1 to n, and n equals 1, then you start with 1 and you're already there, right? You start here with 1 and you're already here, so there's nothing to add at all, right? So our left side equals 1. Now our right side is going to equal n, which is 1, times n plus 1, it's 1 plus 1, that's 2, divided by 2. Now the 2's are going to cancel out, you see, that's 2 and that's 2, cancel by division, and this is equal to 1. Left side equals right side, so the claim is true. Now we're not done. But at this point, you may be thinking to yourself, hang on a second, Tristan, you taught me that if you're trying to prove something which is universally quantified, proving that it's true for any particular value is not sufficient, right? You can't just do some examples and say, hey, look, it's true, because that doesn't prove it for all, right? Well, that's correct, but that's not all we're going to do here. There's more to this than just a base case. So the next, a proof by induction has like 2 parts. The next part is called the inductive step. And the inductive step always starts with an assumption. It's going to seem a bit strange, okay? It begins with this. Assume 1 plus 2 plus ... plus n is equal to n times n plus 1 all over 2 for some arbitrary positive integer n. Well, that seems a little strange, Kristen, because that's what we're trying to prove, right? Not quite. This is for some arbitrary n. I'm not assuming that this is true for all n. What we're trying to prove is that this is true for all n. Any positive integer, that's for all, right? So I'm just assuming that it's true for some n, all right? And it doesn't matter which one. It's got to remain arbitrary because we want it to be we want to be able to generalize this. What we're going to do now is we're then going to examine the case for n plus 1 and prove that the claim is true for n plus 1. Okay, so we're assuming this, and now we're going to examine n plus 1. Now, if we take n plus 1, then the left side of the expression is going to equal 1 plus 2 plus ... plus n and then plus n plus 1, right? Got that extra. You're adding on one more number. And what we want to do now is we're going to try to prove that this is equal to the right side. And we're going to use our assumption. This is sometimes called the inductive assumption, right? It's the assumption you make in the beginning of the inductive step. And we want to use it somehow. So it helps to think about it like you're trying to find a copy of the nth case embedded in the n plus first case. So here's the left-hand side for the n plus first case, and a copy of the nth case can be found right here. Sorry, right there. So what I'm going to do is I'm going to use my inductive assumption, and I'm going to replace that with the expression n times n plus 1 all over 2. Just like that. Here, let me write it over so you can see. N times n plus 1 all over 2. And then that is still plus n plus 1, like that, right? So that's that there, I can say by the assumption. Okay. So now I have to do a little bit of algebra. What I'm going to do is add these two terms together by using a common denominator. I'm going to get n times n plus 1 and then plus 2 times n plus 1. And that's going to be all over 2. So you can double check that. That is just, common denominator of 2. Make that all a bit smaller. And now what I want to do is I want to factor out n plus 1. I can see here I have n plus 1 here and here. So I'm going to factor that out. So I'm going to get n plus 1. And then what I have left over after removing it from each term is n plus 2. That's all over 2. Now this, n plus 1 times n plus 2, might look like not much at all, except that is the right-hand side of the expression when you replace n with n plus 1. So if it was n plus 1, it would be n plus 1 and then n plus 1 plus 1, which is n plus 2, right? So what we have here is the equivalent of the right-hand side with n plus 1. So that was our goal. Okay, so we were able to prove that left equals right. So it's true for n plus 1. Okay, then we've done the two steps. We've done the base case, we've done our inductive case, and essentially what we have is sort of, we've proven kind of a recipe. It's almost like induction is not so much to like prove it for all, but it does prove it for all n, but it's like you're proving a recipe for proving it for all n, right? What we've done is we've shown it's true for 1. And then we showed if it's true for n, it's got to be true for n plus 1 as well. So if it's true for 1, it must be true for 2. And then if it's true for 2, it's got to be true for 3. If it's true for 3, it's got to be true for 4, and so on. In fact, sometimes this is likened to like dominoes, where what you're basically proving is that you can show that it's true for the first number, and then if you know it's true for the first number, it's true for the second number, and so on and so on and so on. So it really is like, hey, I can knock down the first domino, and that will prove it for me down the line, down the line, down the line, and so on. And then it's true for all, because all the dominoes fall down. That's kind of the idea. So we can actually take just these two parts and then say for 1 plus 2 plus dot, dot, dot. N does equal n times n plus 1 all over 2 for all n in Z plus. All right. So that's the end, QED. But what I want to do now is sort of describe a more generalized, like a more general form of a claim that can be proved by a mathematical induction, and then show you, like, kind of like break this down and analyze it, and just like break it down into the parts and show you a way of conceiving of proof by induction more generally, sort of abstractly, so that you can apply it to other types of problems. All right, so the type of claim we'll be using, that we will be proving using induction, is something like for all n in some sort of set that's similar to Z plus, but I'm going to use Z plus so we can start at 1. Okay, for all n in Z plus, something is true about n, p of n. Okay. Now, right there, that is a propositional function. It's a predicate, just like we learned about in chapter 1. It's not a function whose output is a number. It's a propositional function with a truth value. So P of n stands for some sort of claim about n. So looking back at our, this thing, at this example we did, P of n isn't just the left side. P of n isn't just the right side. P of n is the entire claim, this entire statement about n. Okay, all of that is P of n. Okay. So then the first thing you do to prove a claim like this is you do your base case. And base case is essentially just prove that it's true for the first value of n, which if you're using Z plus would be P of 1. So the base case is just prove P of 1. Now that's all you need to do. In some recursive structures, you need to like establish more than one base case. Just an example for you would be like the Fibonacci sequence requires you have 2 base cases. You need to know the first 2 terms in the sequence to get the next one. Right? That's another sort of recursive structure. With proof by induction, you usually just need 1 base case, because then each value, each case proves the next. So that would be our base case, and then our inductive step. So I'm going to label these 1 and 2. And 2, the inductive step kind of has two parts to it, A and B. A is assume P of n for some n in your set. Okay, and in Z plus in this case. Assume it's P of n. That's called your inductive assumption. And then the second part of the inductive step is prove an implication. If P of n, then P of n plus 1. Right? So if the claim is true for n, then it's true for n plus 1. And those 2 parts together are all you need, and that completes the proof. Therefore, for all n, P of n, QED. Okay. So there we go. So this is our first example of proof by induction, and kind of a description of what proof by induction basically looks like every time. The particular format of the claim that you're proving can be all sorts of different things. It's not always going to be summation formulas. Sometimes you prove that something about divisibility of numbers. Sometimes you'll be proving something about like some qualities about a set, and so on. All right. Sometimes you'll be proving an inequality about functions, functions of n. Like you could prove by induction that n squared is less than 2 to the power n after a certain point. So yeah, there's lots of different things you can apply this to, but they all kind of take this sort of recursive structure of like, hey, if you prove it's true at the beginning, and then you prove that whenever it's true for one number, it's true for the next number, then the domino effect causes it to be true for all numbers. And that's the idea.